I hope you enjoyed yesterday, even if it was very long and detailed. I did not expect that it was so long and detailed, but at least you witness an historic event. And the other thing is that, the X particle is the first scalar particle that we found, because the spin zero particle that we have around, like the pi zero, pi plus, pi minus, or the eta, are all pseudoscalar. And I explained to you what it means, pseudoscalar, yesterday or the day before. Just that under space reflection, the wave function change sign. All the particles we have up to now with spin zero are pseudoscalar. That one would be the first scalar, but of course now they have to check all the quantum numbers of that particle. They only saw that there is a resonance with spin zero, but they have to see if it is a scalar or a pseudoscalar or whatever. Please. I did not understand.
Okay, why did he write that equation?
Which one?
The Dirac equation.
Yes.
He didn't have in mind that it's described sphere,
No, this is another. I will show to you that the Dirac equation that we wrote down is Lorentz covariance, so it's another relativistic equation, and I will show to you maybe today that when we go to the non-relativistic limit, it describes a spin 1/2 particle.
Yeah, but when he wrote it, he didn't mean that he wanted to describe spin 1 particle, right?
Spin 1/2. No, it's just when Dirac wrote that equation, he wanted to have an equation that is relativistic, that is first order in T and also in X, so that in that manner there is a chance that it is relativistic covariant and that it has a probability interpretation. Then, as an outcome, he got that it was a spin 1/2. But he did not impose the three conditions I wrote down. In no one of them there was written that it has to be a spin 1/2. We will derive as a consequence that equation describes a spin 1/2. You understand? We will derive it. We have not derived yet. We only wanted three features. He wanted linear in derivative with respect to t and derivative to respect to t to have a chance that it might be Lorentz covariant. That was the first condition. Second, that it has, that psi has a probability interpretation. Third, that it is, so these are the three requirements. We have wrote down these, and as it is linear in derivative of x, and then there is a chance that it's Lorentz covariant, but we have not seen. So these are the only three requirements. He did not want that it describe a spin 1/2 particle. He did not have in mind that from the beginning. We will derive from the form of the equation that it describes a spin 1/2 particle. Okay, so that is a consequence. It's not one of the conditions. He got, as a result, they describe spin 1/2 particle. I might have said this equation will describe spin 1/2 particle, but it's not a requirement, it's a consequence.
Yeah, that's my question, because it's a consequences. But what he wanted, why did he write it?
Why he wrote in that manner?
Yes, to
because
describe what? Just
he wanted to have an equation for a wave function that is Lorentz covariant and that it has a probability interpretation. Why wanted that? Because Klein-Gordon equation does not, Klein-Gordon equation satisfies only this, that is Lorentz invariant, but it has not a probability interpretation. Okay, that was the important thing. So Dirac wanted that to have something that has a probability interpretation. And in fact, he had something that has a probability interpretation because the psi, having an object that has 4 components, he had a psi that is modulo square is positive definite, so it's a probability interpretation. And that one was related to the fact that it was linear in T from the beginning, while the Klein-Gordon did not have a probability interpretation because it was not linear in the derivative, okay? So that were the only things he had in mind. He wanted to get an equation to see if it was possible to get an equation different from the Klein-Gordon and with these 3 features. He was sure that having linearity in delta t, he would get a probability interpretation, okay, for the psi. Then why insisted in having linear also in the x? Because if it is linear in dt and linear in dx, then a Lorentz transformation might have a chance to be an invariance of the symmetry, okay? Like, for example, the Klein-Gordon was second order in T, second order in X, and then it was Lorentz covariant because the second derivative in T goes into the combination of second derivative of X and so on. If you start with the first order derivative, you must have first order derivative because, you know, these are like vectors that are rotated and they don't rotate into ddx squared, but into ddx at most. So that are the requirement he wanted, okay? Not that a spin 1/2, he got as a result that he described as spin 1/2. But before going to that, okay. Let's start where we yes, please.
I just want to know a little bit about the particle that weighs on yesterday. What's exactly the physical difference if we find a particle with spin 0 and it is a scalar?
I mean, in the X things, it was a particle that was needed in the framework of the standard model. They had found, there were the hypotheses that there were 3 families of quarks, and they found 3 families of quarks. There were the hypotheses there were 3 families of leptons, and they found all the leptons in the standard model. In the Weinberg-Salam standard model, there was this. But then there was another particle, it was a scalar, that is the X scalar, is a scalar particle that never seen a scalar particle, that never found a scalar particle, but that scalar particle is very important. Why is so important? It's much more important than the quarks and the lepton. Because, you know, there is a gauge invariance in this model, and it's not the gauge invariance of electromagnetism, but it's a larger gauge invariance. It's a gauge invariance that is not only the one of electromagnetism, but is a larger one that includes also the one of the weak interaction. Now, the point is that you have to start with all the particles without mass if you want gauge invariance. But we know that the quark have mass. We know that many other particles have mass. So you have to invent a mechanism to give mass. So you can give mass either directly, but if you give mass directly, it's like giving mass to the photon. You lose gauge invariance. So X, and actually a month before him, the other person who came down to meet him and shake his hand, Englert, he and his former teacher, Brut, that died a few years ago, did it a month before. Yesterday I checked the date. Brut and Englert in Belgium did in June 64, and X did in 64. And in 64, but in July, a month after, but they did not know each other at that time. There was not the internet where you put your paper in and immediately you see. And so he did a month before, but totally independent, everybody recognized. And then in October, 4 Americans did the same, but they quoted this paper, so it means they had seen this paper, but now they claim that they also want a piece of the, would be Nobel Prize or something. There are Goralnik, Hagen, and some, but I mean, they did in October, and they quoted the paper, so it means they had seen the paper. If they were smart, at least not to quote the papers, and they did something slightly different. But anyhow, so it's very important, that particle, but not only because it's the first scalar particle that we had ever detected, but also because it's a particle that, via what is called Higgs mechanism, give mass to all the other things. And the things is like the following. Imagine that instead of having particle physics, you have a normal potential. And imagine that you have a potential that looks like a Mexican hat. Okay, like a Mexican hat. And the ground state are these points. Now, what Higgs proved is that this, imagine it is the potential that the Higgs field, so the Higgs field obey the Klein-Gordon equation, and imagine that to the Klein-Gordon you add a potential, okay? So this is a V of phi. You could choose as ground state any of these, so there is a degeneracy because they are all at zero of the potential. What happens is that if you choose one particular one of these, that means you choose a particular vacuum, then via mechanism that he invented is too complicated for you, you will learn next year. Then if you choose a vacuum because the system sits on a particular vacuum and all the excited states that are built out of this Hilbert space, then the quark get a mass, the gauge field get a mass, because you know the weak interaction are short range, so the analog of the photon for the weak interaction must be massive as they are short range. So you have to give a mass to the gauge boson and so on. And that is what he did, but he did only for the U1. Then Weinberg and Salam independently, well, Salam did 6 months later, but I mean, at least published 6 months later. What happened is that Weinberg and Salam extended to the full gauge group of the electroweak interaction. So more than the scalar particle that they found is important, the Higgs mechanism. But the Higgs mechanism works only if you have a scalar particle that they called Higgs boson. They should have called Englert-Brut boson. But what happened is that Weinberg did not know the paper of Englert and Brut. That was a month before. So he started calling it Higgs particle. And in fact, there is a nice article on the New York Review of Books that is on the library, is one of the newspapers that is on the library. There was a nice article a month ago where Weinberg said, it's my fault that I called it. It's not the fault of Higgs. Higgs, 2 months later, he was informed that there was this other paper, and he has always acknowledged this other paper of Brut and Englert. It was Weinberg who did not know, and in this paper of 67 said that the Higgs mechanism, and I think it's also due to the fact that the Anglo-Saxon, that means American and English things, they make a word apart, and especially in those years they were never looking at the paper coming from other countries. That was a sort of, but then Brut and Englert, Brut actually was American, even if he had moved to Belgium, started banging their fist and said, come on, we did it a month before even. This is the 2 papers. So, but they did independently, so I am sure that at least they will, if they give the Nobel Prize for I think they will wait before giving the Nobel Prize, even if Higgs, you know, when he said, I am happy that this happened during my lifetime, because it seems he's been sick for several years and he's not well, so that's, they better rush up otherwise. Tell me.
Why the photon doesn't interact with Higgs field?
No, the photon interacts with the Higgs field. You have seen that there, they said that the main decay channel was the Higgs going into 2 photons.
Okay, but why the photon doesn't have mass?
No, the photon does not have mass because of gauge invariance. The photon does not have mass because of gauge invariance. The Higgs, So take the X at 25.6, and this has a huge mass. It goes into 2 photons, each of them with an energy of 23 Jeff, 62.3 Jeff. So it's not that a massive particle cannot go in massless particle. You know, we have proved, this course proved that energy and mass are equivalent, so it goes into massless particle, but with this energy. So they turn all the mass of the X into energy. You understand? So, no, you don't understand. Tell me what is wrong.
Because each part, okay, when the particle interact with the X boson, no, okay, the X boson or the X field, this field transfer the mass to the particle.
No, the mass is not conserved. That's the point. It's the energy that is conserved.
But our particle get the mass.
No, the X is created by, is a field, okay, that is created and it has a mass and is created from the vacuum and it has a mass. That particle can be transformed into particle without mass because mass is not conserved. That is the special relativity main things that I want. Good that he has that question. What is conserved is energy, not mass. In fact, Einstein proved that mass can go into energy and vice versa. So here the mass of this object, the mass of the X field, this is the main decay mode. Yesterday they said we have studied heavily this. The X going into 2 things, into 2 photons, and it goes into 2 photons. There is nothing wrong. They don't have mass because the photon cannot have mass, but it can have all the energy you want. So it's important that it carries away the same amount of energy as the original X. So remember, mass is not conserved. It's not a quantum number that is conserved. It's energy that is conserved. And energy is conserved because it's related to that symmetry that is time translation.
Okay, we know that to generate a field we need a mass.
No.
The particle, okay. But it's a particle.
No. As mass is not conserved, the X field come out from the vacuum as an excitation without the vacuum having mass. You will do, when you do field theory, you know, are concepts that are very difficult to swallow for the moment. But, I mean, there is a vacuum that is full of particle and antiparticle, and what happens is one of them can pop out of the vacuum, and it can pop out of the vacuum with its own mass. Okay, because mass is not conserved. It's important that in the vacuum there is enough energy to give this particle some mass. Please. Then we have to stop, otherwise we don't go on. We are quite behind schedule, so. If you don't, I am deaf. It's true. I have one. Please shout. Shout.
So the mass of
I cannot hear. I am not going to answer.
the mass of the Higgs boson is around 125. So I'm confused because wasn't this energy accessible before? Wasn't this energy accessible because I think it was they were doing experiments with energy above this one. So why was it not found
Before?
Yeah.
No, it was not found before because, you know, maybe there were signal of something at 125. In fact, at Fermilab, they saw a signal of something at 125, but they did not have enough luminosity. Remember that they talk about luminosity. Luminosity is the number of particles that you have per bunch, and you have to have many bunches. In the accelerator, there are, I don't know, many million bunches separated one from the other, and the luminosity is very high. It means there are a lot in a very small section. Then you produce many of these, and then the peak increase and you can see it. And yesterday, in December, there was another announcement that people might say, oh, come on, this is a small mistake in taking data. But now they are sure it's not a mistake because they have found that the chance that this is a fluctuation is 1 over 3.5 million. So when they said 5 sigma it means the chance that this is not a fluctuation is 1 over 3.5 million, so it's not a fluctuation. That is why the director of CERN, that was that man that introduced them, said at the end, I think we can say we have it. Because when they, and why the applause was when they showed the 5 sigma things, because that in experimental physics is the sign that something is not a fluctuation but is an event, is a permanent event you have to take. Now, why they did not have the energy at 125? It was available also at Fermilab, okay, to produce something like that. You don't need 8 TeV like they use, but they had 8 TeV, so a lot of energy, and also a lot of luminosity. That means the number of particles they managed to squeeze into 1 centimeter cube were many more. So you have seen when, for example, they said, well, we had an event with 25 scattering. It means in 25 points, it means there were so many particles into a cubic centimeter that there were, and another cubic centimeter coming because they scattered one against each other. There were so many that there were 25 events just in one. So having more events, the statistics get better, you understand? So it's the luminosity that main things. At Fermilab, they did not have not enough energy, but did not have enough luminosity. And the luminosity is the most difficult things to get because you have to have to squeeze the beam, okay? And second, be sure that the magnetic, and you know, to squeeze the field, you need to have magnetic field extremely strong. And that is what they have, and also extremely stable and extremely precise. And in fact, you know, one of the main things that happened at CERN when they started the LHC machine, there was a problem in a magnet, and that magnet distorted the other and ruined the other just because the magnetic field there are extremely strong and they can bend anything like so. Okay, now please let's stop here. We will maybe do some other time, but we have to continue with the program. Okay, so these were the 3 requirements that Dirac wanted, and the equation he postulated, just postulated, and then went on to write detail was the following one. Let me write in the form that is the best one for you. Okay, IH psi dti. These as many components, sigma HC over I sum tau from 1 tau from 1 to n alpha 1 ddx1 plus alpha 2 ddx2 plus alpha 3 ddx3 sigma tau psi tau plus mc squared tau from 1 to n beta sigma tau psi tau equals 0. So we had 4 matrices, alpha 1, alpha 2, alpha 3, beta, and we have a psi that had n component, psi 1, psi n, with a scalar product being defined in this manner. Yesterday, and this positive definition. Yesterday what we proved is, so sigma is the component. What we proved yesterday is the following, that if we want, if we take the second derivative with respect to time and then propagate it, second derivative here, and then here put again the Dirac equation in, we find out that in order for the usual mass shell mass shell relation to holds. Okay, so that was another condition that Dirac wanted. Let me see, because I missed some paper. Okay. You know, this is this, and we want that the energy is equal to P squared C squared plus M0 C4, the usual energy relation, and we wanted at least at the operatorial level where this is IH ddt and this is IH ddx according to the various things. Then if we wanted this condition to be satisfied, at least at the operatorial level, then as this is the second derivative with respect to time, we have to act on the second derivative with respect to time. And in order for this to be satisfied, it's an operatorial relation. Yesterday we proved that there were some relations that had to be satisfied by the, first of all, as this object with the I is Hermitian, also the alpha I have to be Hermitian. Alpha I daga is equal alpha I, beta daga is equal beta, and then we found that for this to be satisfied at the operatorial level, the alpha and beta have to satisfy some anti-commutation relation that were the following one. Let me write them in the form. Okay. Okay. We found this is to be Hermitian, and for these induce the following relation: alpha I alpha j plus alpha j alpha I equal to delta ij, alpha I beta plus beta alpha I is equal 0. Then from the first one you get that alpha I square is equal to the identity and beta square is equal to the identity 2. Okay, so these are the conditions that have to be satisfied. This is a consequence of the first one. And if I ask you in the written final exam, where do these conditions come from? They come from this, okay? So if I and j are not equal, it means this anti-commute, the alpha anti-commute. So you often hear the Dirac matrices anti-commute. These are called Dirac matrices. And there are various species of Dirac matrices, not only this alpha, but there are many others that you can. What we proved yesterday is also this. We proved that the trace of alpha I is equal 0, and the same the trace of beta is equal 0. And because of this relation, the eigenvalue from here, the eigenvalue can only be plus or minus 1. Then having the trace equal 0, it means n is equal to an even number. So we start searching for realization of this. That means which matrices do this. And the matrices that anti-commute by themselves are, for example, the sigma matrices, the Pauli matrices. They anti-commute, so they satisfy this. Okay? But the point is that there are 3, while I need an even number because of this property. So having found that the traces are 0, so they are Hermitian, the anti-commute. Anti-commute, it means this often, this is what it meant, anti-commute. That means if the two indexes are different from 0, are different from each other, then the product of 2 is equal to the minus the product of the other in the inverse order, and the same here. Okay, so this is where we got, I think, the other yesterday. Now, we also find out which is a realization of this. So the sigma matrices are not okay, but there is another realization that works, and is the following: alpha I equal sigma I 0, 0 where the sigma I are the Pauli matrices, and beta equal the identity minus the identity. So these blocks are 2 by 2, and altogether the matrices are 4 by 4. What I think I did not say, and why this works because, you know, the sigma matrices have this property, sigma I, sigma j, plus sigma j, sigma I is equal to 2 delta ij I. Okay. Now, what today I want to show to you is that this is not the only choice. You could do any unitary transformation of this matrix, and this relation would still be satisfied. Okay. Okay. So, for example, let me cancel somewhere. I'll cancel here. So that one is not the only realization, but let's say it's the most simple. You could, for example, take alpha I prime defined as u, alpha I u to the minus 1, and, or u dagger, and beta equal u, beta u dagger, with u a unitary transformation. So let's define this other quantity, and all those relations will be satisfied. And this is very easy. Let's take, for example, the first one. Let's see if this unitary transform matrix satisfies the first relation, the first anti-commutation relation. Well, you have the following things: alpha I prime, alpha j prime, plus alpha j prime, alpha I prime. Let's see what they are equal. They are equal to u, alpha I, u to the minus 1, because it's unitary, so u dag is u to the minus 1. Then you have u, alpha j, u to the minus 1, plus u, alpha j, u to the minus 1, u, alpha e, u to the minus 1. Equal, let's see what is equal. First of all, these two cancel. These two cancel, so here we have that this quantity is equal, all these is equal to u, alpha e, alpha j, plus alpha j, alpha e, u to the minus 1. But we know from the previous relation that this is 2 delta ij, u to the minus 1. Well, this is just a number, this 2 delta. The u can pass through, and so we have u to the minus 1, 2 delta ij, and this goes away. So that means also the alpha prime satisfy the same commutation, and it's easy to do for all the other. You can do as a simple exercise. It's not homework because it's too simple, and check that also the other are satisfied. So you can do unitary transformation and nothing changes. Now, the question is, out of this equation, can we derive a 4 currents and have a conservation of a 4 currents? Because, you know, we have in probability interpretation if first we have a 4 currents conserved, and so let's see if we can derive a 4 currents out of this that is conserved. I don't know if I already did that. But let's do it. So I will write here and keep it here, the relation, let's see, this one, and I write here Okay, these are all the information we need. Now I can cancel here. So let's see if we can derive 4 currents from these, conserved 4 currents from that. Let's take this equation. Let's for a moment take away the index. Otherwise you get too much of complication things. So let's only indicate the matrix. We know this is a vector 4 by 4. This is a this is a column vector 4 times 1. This is a matrix 4 by 4, and these are matrices 4 by 4. Apply on a vector, take away the index of the vector, and so on. Now let's multiply this equation by psi dagger. Then, and psi dagger, it means if this is a column, this is a row, and this is a row down psi 1 star, psi 2 star, psi 4 star. Okay, so let's multiply on the left by psi dagger. We have I h bar psi dagger d psi dt equal h c I psi dagger. Let's sum over the various matrices I from 1 to 3. So we have alpha I ddx psi psi plus m0 c square psi beta psi dagger beta psi. First. Second, let's do the Hermitian conjugate of this Dirac matrix. This Dirac, this is not equal 0. This is the equation. So let's do the Hermitian conjugate of this. If we do the Hermitian conjugate, so Hermitian conjugate of the Dirac equation. If we do, you get, okay, Hermitian conjugate, it means you have to transpose and do the complex conjugate. So you transpose these and you get, you do the complex conjugate, you get minus IH d psi dagger dt. I'm doing the Hermitian conjugate. Then the same here, and then we get equal minus HCI. Then remember the alpha are Hermitian, so we get I from, here we have to put, no, I put it here, I put it here. So sum over I from 1 to 4 d psi dagger dxk alpha k dagger plus m0 c square psi dagger beta dagger. When I do the dagger, I have to reverse the matrix among themselves, or the vector and the matrix among themselves. Let us remember that alpha and beta are Hermitian, so I can take that away. And now let's do from this equation, let's multiply on the left. Let's take this equation, and let's multiply on the left by psi. If you do, you get the following equation. Okay, so I multiply. I have done the Hermitian conjugate of these. Okay, I can cancel this thing. So, of the Dirac equation, I've done the Hermitian conjugate. I have been careful to reverse the order when I do the Hermitian conjugate and to do the complex conjugate. Now I multiply on the left by psi. Now this is a row vector by a 4 by 4 matrix times a vector multiply on the left, so that is a column, and then I have the normal things. If you do, so do that calculation, and you get minus IH d psi dagger dt psi equal minus HC I sum I from 1 to 4, from 1 to 3, from 1 to 3. So here from 1 to 3, because it's the alpha only sum. So let's put this alpha I like here, This line, how I got it? I got as doing the Hermitian conjugate of this. Here, and then I multiply on the left by psi. So this equation is the Hermitian conjugate of that one. And then I multiply on the left by this. Okay? Then what you get is what I'm writing down here. And I multiply everything. That means left and right hand side. So here I get the derivative respect to t of psi dagger times psi multiplied by this. So I get d psi dagger dx psi alpha I psi plus m0 c squared psi dagger beta psi. Now let's subtract. So I have these two equations. Now let's subtract the second one from the first one. If we do, so let's subtract this from this, and we get the following things. Remember, alpha and alpha are the same, and if you subtract, no, I subtract the second one from the first one. Then what I get, so I subtract, put a minus, the second one from the first one, I get IH ddt psi dagger psi equal HC over I sum ddx I psi dagger alpha I psi. Okay? When I subtract these two goes away. These two sum up because there is a minus, and these two sum up because there is, and so there is a 2 here. When I sum, there is a 2 here that cancel, and these two instead cancel against each other. So you are left with this equation. And this equation can be interpreted as for current conservation, because if I interpret rho as psi dagger psi, and I interpret the current jk as c psi dagger alpha k, okay, alpha I psi. If I interpret these two, this piece as a probability density, and this piece is a current, then this equation is nothing else than d rho dt plus divergence of j equals 0. And this is a for current conservation. Okay, so behind the Dirac equation, there is a for current conservation, but the beauty of it is that this is positive definite now. You see? So one of the requirements was satisfied. He proved that one of the requirements was satisfied, and that was not clear from the form he started. But you know, he was smart enough to say, let's start from the first order equation, the most general one, where the coefficient, you know, if you, it was the most general one beside the H and the C and so on, because he had alpha, beta coefficient, and he said, let this be matrix, let psi be a vector. So the most general things you can imagine, and then to satisfy the energy mass relation, at least at the operatorial level, you have to have relation between the alpha, and then looking at the equation, he could derive for current conservation, and then these, that is, the density is positive definite, differently than in the Klein-Gordon. In the Klein-Gordon, this was not positive definite because we started with a second order derivative in t. Go back and review the calculation, because this is really one of the most important parts of the course to understand this difference, okay? Now, of course, you know very well how from this relation one can derive that there is a total conserved quantity. So now I cancel here. Okay, so the equation is d rho dt plus divergence of j equals 0. Now, how do you derive that there is a conserved quantity? When you have a 4 current, how do you derive? Is the usual things. You integrate 0 dt over d3x plus divergence of j over d3x. All this is equal 0. But now, here you can bring this ddt out, and you have rho d3x. And this one, you use Green theorem, and instead of having a volume integration, you have a surface integration over the surface that surrounds the volume, and you have j times n, where n is a vector perpendicular to the surface. And then if you take the surface to infinity, the currents, and you suppose the fields as they are normalizable, they go to 0. So this part goes to 0 when you send s to infinity. And then what you are left is that ddt rho d3x is equal 0. So there is a conserved charge that is this. I call charge, but in this case, the rho is psi daga psi, so it's positive definite. And psi daga psi means psi star 1, psi 1, plus psi star 2, psi 2, plus psi star 3, psi 3, plus psi star 4, psi 4. Because there are 4 components. You can say, well, you only said it's even, so we could have 6, 8, and so on. Yes, we could, but we stick to the smallest one, because we will see that the smallest one, and we will analyze the smallest realization of the Dirac matrices, okay? Now, if you want to write this as d mu j mu equals 0, then what happens is you just promote the j0 to be c rho, and you get 4 current things. So that means this one is equal to this if you promote c rho multiplied by c to j0, because you remember that x0 has a c here. So you have to multiply by a c by cancel, and then this object is the j0. Now, let's, the first case when you have an equation, like imagine that this is like the Dirac, this is like the Schrödinger equation, you solve the free problem, so the free particle case. Let's solve the free particle case. Free particle, it means we don't add any potential. That is the equation of motion for the free particle. So let me cancel. And why we solve the free particle? Because in most cases we will have to handle, and there is enough physics already in the free particle case to solve it. Well, first of all, we will look for stationary solution, like we did for the Schrödinger equation. That means we separate the energy part, the time part. That means we look for solution of this form. So this is not, you can say, but this is not the most general solution. But it's easy to prove that the most general solution of that is a linear combination of this with different value of the energy. Okay? So it's possible to prove so that psi x of t is a linear combination of psi, let's call A, where A is not the index of the things, is many different wave function, exponential minus EH bar AAT. So the most general solution is a combination of this form. This is possible to prove it, okay? So as the most general solution is a linear combination of these with different energy, you see I put an index here, it means different energy. And here different space parts. So this is not the index of that as a vector, but it means I choose different function. Different. Remember that this was a vector. Okay, I choose different one. It's possible to prove that this is the most general solution. Do as an homework. that is a simple homework, but sorry that I give many homeworks, but they are small. They are very. I need a pen from some of you. Thank you. Okay. So as the most general solution is a linear combination, let's just study one of them. You know, if you plug this in, what happens? The derivative with respect to t, what it does, it brings down minus IH times E. Minus IH times E, there is I minus I, give plus 1. H in the denominator cancel this H, and here you are left with E. So you get E psi of x times the exponential. But the exponential remain also here and here, because nothing touches this exponential, so we can cancel it. And at the end, the equation is this. Let me write here with the, the normal thing. So C alpha P, where P is the operator of derivative, plus M0 C. Let's see if I need beta psi of x. Okay, so this psi of x is not the full wave function, it has the exponential, but the exponential drops. And you know, this, if you look at it, is actually the Dirac Hamiltonian. The reason he put an F in the book means free. I thought it meant fermions, but instead it means, but I don't like it, so I call H Dirac. This is the Dirac Hamiltonian. Now let's see if I have, there are problems with C or C square. So check if here there is a C square or a C. Let's see, this is V. So here we have VC square, then alpha is a C, so there should be, this is an energy, so there should be H square. The second thing, so remember, we are trying to solve that with these ansatz. Ansatz is, by the way, is a German word that is often used in physics. It means attempt, hypothesis. Okay, that means we do this, we choose not the generic solution, but one of these form. And then this is the stationary Dirac equation. Like you have the stationary Schrödinger equation. This is the stationary Dirac equation. Now let's remember that psi, was a 4-component thing, psi 1, psi 2, psi 3, psi 4, because we chose n to be 4. Well, let's split these in the following manner. Phi, chi, where phi and chi are 2-component objects. So phi is psi 1, psi 2, and chi is psi 3, psi 4. let me write them in this manner. The reason I do is because from the form of the alpha is then easy to derive the equation. Let's do it. Yes?
We work in an infinite dimensional space, and what is the, and what the difference saying n is even and n is odd?
No, but you see that we are not in an infinite dimensional space.
Here we choose for bet just, just a question.
If n you send to infinity,
Then what the difference?
between odd and even,
There's
you should ask a mathematician, not me. I don't know.
Is there any consequence? I don't know.
The point is, we have to work in an even dimension. Then it doesn't matter if this is extremely large, because, you know, to say infinite, it means nothing. It means larger than any number you want, but even. So infinite, even, it means is a number that is even and is larger than any other number you can conceive of. So now let's put in this parameterization, phi chi. Remember, this is different than the one of the Klein-Gordon one, and don't confuse with that. But let's now put in also the explicit form of the, okay, let's put in the explicit form of the alpha. So here I put the alpha. And why I put the explicit form? Because now I have 2 by 2 vectors. And so the sigma, I know where it acts. Okay, because these are block 2 by 2. So if you do, from this equation, you go to the following one. E phi chi equals C 0 sigma 0 times P phi chi plus M0 C square I 0 0 minus I phi chi. Okay. So now you equate the upper 2 component and the lower 2 component on the left and the right hand side. So you see this is a 4-dimensional things, but of course if you work out the components, you will have an upper 2 component and a lower 2 component, and the equation you get are 2 equations. E phi equals C sigma dot P chi plus M0 C square phi, and then you have E chi equals C sigma dot P phi minus M0 C square chi. Okay, so what I have done, this is a 4 by 4 things, and I equate component by component, but these are objects are 2 by 2, this 2 by 2, so you get the upper equation is this and the lower equation is this. Note that they are coupled equation. The chi and the phi get coupled because this object, when it acts on the vector, it goes and pick up chi. So it does sigma times P chi. But sigma is the 2 by 2 matrix that acts on this vector that is the 2 by 2 vector. But you see phi and chi get coupled. Now let's do a further simplification like we did for the free particle in the Schrödinger case. We do a further simplification that we choose phi and chi to be of the following form, to be eigenstate of the momentum. Let's fix the momentum, exponential IHP times x. Okay, so I do a further simplification. First, I chose stationary solution, means at fixed energy. Now I choose solution at fixed P. Okay, so P is a number and is fixed. So let me cancel and let's see what I get. Well, I can cancel also these. I plug in this into this equation and into this equation. Phi 0, chi 0 are something that now don't depend on anything because the parameterization on X we have pulled out. So what we get is the following things. So plug it in and then rearrange things, and you get the following two equations. E minus M0 C squared, the identity times phi 0, minus C sigma dot P chi 0 equals 0. And the second equation is C sigma dot P times phi 0 plus E plus M0 C squared chi 0 equals 0. So you see, these are two equations for which are the unknown. The things that we still don't know, despite having fixed the energy and having fixed the momentum, are these that are now coefficient, constant coefficient, but we have not determined them. They have to satisfy this equation, and we know they are 2 by 2 coefficient. So how I got these with these strain things, I plugged that in, and then I brought on the, so I brought that in here, but then what I did, I made sure that all the phi are on the left-hand side and all the phi are together. So there is a phi here and a phi here, and it becomes this object. The chi is only here and is left the same, okay? But I brought on the left-hand side, so there is a minus. The same here, I made sure that all the phi are on the same side, so I brought that on the left-hand side, and I get a minus, and then E, and all the things that multiply chi, because these are known coefficients. So now this is a matrix equation in which the unknown are this object, and the coefficient are the other. As they are inhomogeneous, is equal 0. So these are the unknown. When you have two equations, linear equations, they are linear. These are coefficients. The unknown are these. This is like x and y, and this equals 0. You know that there is a solution different from 0, only the determinant is 0. Okay, so we have to take the determinant of the coefficient and put equals 0. We get E minus M0C times I minus C sigma times P minus C sigma times P E plus M0 C squared, the identity of this determinant is a 4 by 4 determinant because these sigma are 2 by 2. I impose that is 0. In order to have now, if you work out this equation, let me do the detail because once it's better to do the detail. So let's work out this determinant. You know, is the usual things. And you can do in blocks the product of this minus the product of this. And what you get is E squared minus M0 squared C4 I minus C4 sigma dot P times sigma dot P equals 0. Now the difficulties is this space, but there is an identity that I write down here, very well known identity for sigma matrices, that is if you have sigma multiplied by a vector A, product sigma multiplied by another vector B, this is equal to the scalar product of A times B multiplied by the identity in 2 by 2 plus I sigma scalar product of A wedge B, where these, okay, this is a well-known identity in sigma matrices that for sure you have seen when you did the sigma matrices. If you have not seen it, work it out at least to see. So A and B are vectors. sigma are 3. Okay, so these basically are the linear combination of 3 matrices, sigma 1 A1 plus sigma 2 A2 plus sigma 3 A3. And here is sigma 1 B1, sigma 2 B2, sigma 3 B3. Is the product of 2 by 2 matrices, linear combination, you do, and is equal to a 2 by 2 matrix. That coefficient is A times B. A and B are vectors, so this is a number, multiplied by a 2 by 2 matrix. And then here you do this. This is the vector product between these two vectors, so you get a vector multiplied by this matrix. Multiplied by this matrix, it means sigma 1 and the first component of this, sigma 2 and the second component of this, sigma 3 and the third component of this, okay? Okay, so if you use that identity here, you see we have exactly A and B are P and P. Now, if you do that, what you get is that basically you get only the vector product is 0. So you are left with this, and so what you get is A M0 C squared 4 multiplied by the identity minus C squared P squared times the identity equals 0. But this is the well-known mass-energy relation. Am I right? There is something. C squared. There is a C square here, most probably, right? Yes. And this is the famous energy relation, mass-energy relation. So it means, what does it mean, all these tour de force that we did? That if we want the free energy solution with that constant energy at constant P, then to be a solution, you know, to be a non-trivial solution with this coefficient different from 0, the mass-energy relation must be satisfied. This is very important. Because remember that Dirac was one of the things he wanted. He wanted at the operatorial, that the mass-energy relation be satisfied at the operatorial level implied this relation. But that is only at the operatorial level. Is it satisfied also at the C number level? We put in and use, you know, we have used this. That means we have used the fact that it was already satisfied at the operatorial level, the mass-energy relation. And as a consequence, having used this, it means it was satisfied at the operatorial level. At least for the free particle, we find out that it's satisfied, if we want a non-trivial solution, also at the C number level. Okay? So that is very important. He recovered. That means his equation was a relativistic equation. That is a very important sign. But you remember, everything comes from this. Otherwise, it would not come. Now, from this relation, we get that the energy can have two values. A, let's call P, is equal to plus or minus the square root of M0 C4 plus P square C square. Check with all the C. Okay. So there are two, also here there are two energy levels. That means there are negative energy, and that was a problem. That was a problem, but we will talk about this problem. That means he has a positive probability, the Dirac equation, but he ends up having negative energy like in the Klein-Gordon. So he has to find a solution or an interpretation of the negative energy. Okay. So now let's remain at this level. We have seen that there are solutions different from 0 if this is satisfied. We have proved that the energy are 2 and have the same form as the usual one. But now let's go and find chi0 and pi0, because we have to find their form. You know, so this was satisfied, and now let's go. Now, if this, as this determinant is 0, it means these two equations are the same. One is a linear combination of the other. So it's enough if we solve 1. So let's solve one equation. And for example, let's solve this equation. The determinant is 0, so one is equivalent to the other. Then we get that chi0 is equal C sigma dot P over M0 C squared plus EP phi 0. Okay, so we have solved this equation. Check the various C because I might have lost some of them. This is a 2 by 2 vector that depends on the other, so fixed. Once you give me this, automatically you get the chi0 because this equation is satisfied and this equation is satisfied. So this is the relation between the upper and the lower component of our solution. Remember that our solution had this form, and the chi0 and phi 0 were the component after I had factored out the thing. So now that we have these, phi 0 is arbitrary. It's chi0 that is determined. So phi 0 is a constant and is a 2 by 2 vector. So it can be done by two numbers, u1, u2. Call this u. Okay. And then we will require also that this normalize, so u1 star u1 plus u2 star u2 equal 1. Let's make this choice. And the other things, let's remember that here I could put plus and minus, okay? So here, let's put a coefficient lambda that can be plus or minus because I could choose both of them, and here the modulus. Okay, I could choose, there were two energy I have shown, so I could put. And then the two solutions are, let's now write down the full complete solution, psi of xt, that was phi 0, chi 0, exponential IPX over H, exponential minus ET over H. Okay, this was the space part and this was the energy part. Let's now put in what we have. Now we know that chi 0 is related to phi 0, and we know that phi 0 we have chosen to be some vector u arbitrary that we have. So this one is arbitrary, the other is related to this because of these two equations. So what you get is some normalizing factor that I call n. Okay, I keep a normalizing factor even if I have normalized these because it might be that the full 4 by 4 vector is not normalized. So n, then I have phi 0, but phi 0 is u, so u. And then I have the other that is c sigma dot p m0 c squared plus lambda EP exponential. Now I put all this together. By the way, I put all this together. IPX minus lambda EP, because here also there is EP, and of course it can be positive and negative. Then I should choose I lambda modulus EP, I lambda modulus EP over H bar. And then, so this is exponential of this quantity. And then I divide just for convention, we are in 3 dimensions. Okay, it doesn't matter, this I did not put it before, I can reabsorb in that, but we prefer to keep it in this manner. Okay, so we have solved the free Dirac equation, and the solution is this. There is, sorry, here there is a u. Okay, because this is chi. The lower component is chi. The upper component is arbitrary, is u, because I choose phi 0 to be u. Then I have the normal space part and the normal time part. Okay, so this is chi 0, and this is phi 0. So this is the generic solution for the free Dirac particle. you see it's quite complicated with respect to the Klein-Gordon. If you remember, the Klein-Gordon was quite simple. There were no sigma matrices around. Here instead we have the sigma matrices. This will be the sign of spin, but we will get there when we do the non-relativistic limit. First of all, let's complete these things, finding the normalization. Now, by the way, this solution, we should put label with all the quantum numbers that we have. And up to now, the quantum numbers are P. Once we have P, we have determined EP, because EP is a function of P. But what is left unknown is lambda. So the that is plus or minus 1. So lambda is plus or minus 1. So this is the generic solution, and the quantum number that label these are these. Here I don't put a generic energy. I have to put the energy that depends on that particular P. Okay? Good. Now, let's find N. So this is the solution. Now I want to normalize these things, and I want to find N. Well, what does it mean normalize? It means the following, that psi daga p lambda x on t, psi p prime lambda prime x on t in d3x, we want that is delta lambda lambda prime delta p minus p prime. This it means normalize. These are the quantum numbers. This means normalize. If you plug it in this solution, you know, immediately you find from the P, the 2P, you get the Dirac delta of P. And the rest is just algebra. So plug it in these things. The energy get cancelled. The P, they get cancelled if lambda and lambda bar are and lambda prime are the same. Okay, this one is produced by the exponential, and what is left is only the following things. Okay, n square u daga u, because there is a u here, plus u daga c square sigma dot p over nc square plus lambda EP all square, all these is equal 1. Well, remember that this is 1. Sorry, here there is a u. No, there is no u here. U dagger times that matrix. Okay, anyhow, if you work out this, I will not. You do all the things, use that identity for the sigma matrix and so on, and the result is that the normalizing constant is the following: m0 c square plus lambda EP over 2 lambda EP. This is the normalizing constant, so we were right in keeping something different from 1, because even if the u were normalized, the n was not normalized. Let me see if I did it right. There is a sigma p, there is a u. There is a u here. Now this one. Yeah, it must be the, these objects actually are matrix 2 par 2, so it must be the identity operator. Okay. Anyhow, the final result is this. So we have found also the normalization constant. And so this is the three things, and the normalization constant is square root m0 c square plus lambda EP over 2 lambda EP. Okay, so we have solved completely the free case, and you see what come out. Now, yes?
We divide by something there, 2 pi h bar. Is it just convenience or something?
This one?
Yeah, is it just
Yeah.
convenience?
Yeah, because this is really then the plane wave, normalized plane wave, if there is this factor in the denominator. Now, we said that here we put two numbers, pi and lambda, as quantum number, and in fact, p, we have chosen to have a fixed p, and we have chosen to have a fixed lambda, either +1 or -1. And let's see if there are other quantity. Sorry, I canceled something, but it's on the book. I mean, you don't need to take notes, because I don't think that from the notes, unless you follow the book, this, by the way, is on page, all this is on page 111. Okay. Now let's see if there are other conserved quantity. It means quantity, quantum number with which we can label the free wave function. So you see the difference. If you have to keep in mind the free solution of the Dirac equation, you can say it's like this, the normal Schrödinger kind things, but in front there is a coefficient that is a vector 4 by 4 made by a constant vector u here, a constant vector u here, but multiplied by this piece. Sorry. So all the difference is this piece in front. Now let's ask ourselves if beside p and d or lambda, because E depends on P, so it's not independent, because they have to satisfy the energy momentum relation. And why they have to satisfy the energy momentum relation? Because the Dirac equation satisfies this constraint on the alpha. Let's now see if there is some other quantity that is conserved. And there is. Let me cancel now these, and do I need it? No. So let me cancel now. Let's see if there is some other quantity that the free Dirac equation conserves, so it's a good quantum number. There is, and it's called Olicity. The Olicity is an operator sigma defined in this manner. Take a 4 by 4 sigma 0 0 sigma and multiply by the operator p. So these are operator in and this is a matrix 4 by 4. These are the 3 sigma matrices. This is an operator, but is the operator in the Hilbert space, so in the infinite component space, okay? And there are 3 of them, so you do the scalar product. So basically this object means the following. Sigma 1, P1. P1 is an operator, not in the 4 by 4 space, is an operator in the Hilbert space, plus sigma 2, P2, plus sigma 3, P3, 0, 0, sigma 1, P1, plus sigma 2, P2, plus sigma 3, P3. See, in mathematical language, it means these act on every component of the vector. This is a 4x4, so it acts on the 4 vectors, that were psi1, psi2, psi3, psi4. But while the P acts on each component in the same manner, because it's the derivative with respect to x, sigma acts on these psi1 and psi2, and it modifies them, and the same this one acts on psi3 and psi4, and rotate them one into the other, okay? So there are two different kinds of vector space. There is the Hilbert space. Each of them is an element in a Hilbert space, but there are 4 of them. So here I'm like doing the tensor product of 4 Hilbert spaces. So P acts on the Hilbert space component. That means on this as an element of a Hilbert space. And then there is sigma that acts on this other component and mix one with the other. Okay? So remember, that is the things. So if you want, this in mathematical language is also called sigma matrix value Hilbert space operator, or vice versa. This is a sigma matrix whose elements are Hilbert space operator. Okay, so this scalar product, it means the scalar product between the 3 sigma and the 3p. But then each of them is a different object. This one acts on the Hilbert space, so this one acts on psi1, acts on psi2, acts on psi3, and acts on psi4 in the same manner as derivative with respect to x, right? And sigma 1, sigma 2 instead exchange one component with the other. So they act on different features of the wave function. This is a very important thing, because people write, and then when they have to do a calculation, they don't know how to do. Why they don't know how to do? Because they don't know on which things these objects act. Okay? Well, we will continue tomorrow. We will prove tomorrow that, not tomorrow, next week. From next week, for 2 weeks, we will have 3 times a week, okay? We will have, next week is at 11 on Tuesday, Wednesday, and Thursday, and the same the week after. Okay, then the last week it will only be 2 lectures. Otherwise, there was no manner to. And the homework is due on the 24th, okay.